All right, here's the scenario. Sometimes this is called matched pairs. And I'll go through the 5 steps with you here. This really involves taking from a population, taking a sample to identify the cases, and then from this sample, we're going to collect 2 different measures. We're going to collect a measure before some treatment, let's say, and then we're going to, from that same subject, we're going to take and look at the same measure after, or a similar measure after. And since we have our cases, they might be people, case 1, case 2, case 3, and so on, up to our sample size, n. And we're going to take a before measurement and an after measurement. And then we're going to calculate the difference. And we're going to do a t-test on the difference, on the differences. So even though we have a whole n different data values for the before measure, and then another n sample size for the second set of data, which would be the after, and we could calculate the mean before and the mean after. But what we do instead is we take this before and after measurement and subtract them to get the difference, and then we run a t-test. Remember, a t-test is what we use on the difference of a single claims that are made about a single mean. We will have a single mean if we consider only the differences here. So it's going to be something like this. If let's say that your SAT math score was, when you took it as a sophomore, as a kind of in high school, so I think the first time you can take it, and let's say you get a 530 on your SAT math score. It's the same person. So then this person goes through this treatment. Maybe they go through another year of high school and they learn that way. Or maybe they go to Sylvan Education and they take all these supplemental classes to help them improve their SAT score so that they can, you know, be admitted into their college of their choice, let's say. And let's say that they go through this treatment and then they retake the SAT math score, or the SAT, the math portion, in their junior year, a year later, and they score 550. So you can see that it looks like from their sophomore year to their junior year, they've actually improved. So the difference here is we'll take the 550 and subtract the 530, and we'll get 20. And we would interpret this as a 20-point increase in their SAT score. And we would do the same thing for all the other students. And then we would run a t-test on these differences. That's what the test is going to be. So even though we have 2 groups, two sets of measurements that we can calculate the average for, in this case, we're going to do the differences first because this score is related to this one. If you had another student, let's say student 3 over here, that had a, let's say just a 500 score, we would expect this score to be lower than the 550 because it comes from student 3. Student 1 already had a 30-point better score than student 3. So we would expect this score not to just be some kind of random score, it's related to student 3. So maybe on average they increase 20 points. Then we would expect 520, not 550. So the first score to the second score are not independent of one another. They're dependent because knowledge of what the student scored on the first test would kind of give you a sense of what they're going to score on the second test because they're the same student. That's the idea. Okay, let's go through the steps and then we'll look at some problems. Step 1, which makes this whole process nice because as long as you know that there are 5 steps to every hypothesis test, it's just a matter of getting the language down and the steps down for that particular test. But the first one is to write the hypotheses. So we'll do that. H0 and H1. Oh, here's what we're going to do with this. These differences, these sample differences that we got from our sample size of n, and n in this case is the number of pre-post cases, or maybe I'll just say pairs. Right. So these are not treated as two different values in the sample size. It's just the number of pairs, 1 pair, 2 pair, 3 pair, and so on. Now, we're going to calculate x bar of the differences. And we're going to calculate Sx of the differences. Well, because they're not an x1 bar and an x2 bar and an s1 and an s2, what we're going to use for the mean of the differences, sometimes you'll see this, the mean, and they'll just do a subscript of the differences. Our author just says d bar, but that's the mean of the differences. So you're going to see that number. The standard deviation, S sub d is what we'll use. And then you've got n here. And the other thing is that instead of just mu, we want to know what the population mean is of these differences. And this is the variable that we're going to use. The population mean of the differences between the pre and post scores. And as you know, we only use population parameters in our hypotheses. So the null hypothesis is always a statement of no difference. Let me go back up to student 2 here. Let's say that student 2 scored 525 on the first, went through the treatment and took it the second time and scored 525. If there's no change, if there's no improvement, or if there's no loss of reduction of points, then the difference here would be 0. So if a student doesn't improve or doesn't get any worse, then the difference will be 0. So the null hypothesis is going to be the claim that there's no difference. There's no improvement in this program that they took between their sophomore and their junior year. So this hypothesis will always be the same for us. The population mean of the differences is equal to 0. This would mean no improvement or no betterment or no loss of score, loss of points either. They didn't get better, they didn't get worse. The difference is 0. And if all of these were different and there was no improvement in all of them, in any of them, then what we would have is the sum of all these zeros would be 0. So that's a new variable for you. Notice it's like this little value here is our mu sub 0 value. And it's just looking at one set of data. So we can use a t-test for that because these are numerical differences down here. The alternative is going to be greater than or less than or not equal to, just as before. And the mu 0 value will also be in that alternative hypothesis. The claim usually is the alternative hypothesis, but not always. So it can go either place. And that's how we write the hypotheses in section 11.2. When you define mu sub d, because that is the variable that you have there, so you should define it. It's the mean of the differences of, and then you tell it what you're subtracting. the before and after, or the SAT math score before and after the Sylvan education treatment, or after 1 year has elapsed in high school. And this is always the population mean. Always make claims about the population. Okay. Step 2. That's the level of significance. And there's no change there. Just look for alpha. It's going to be in the problem somewhere. Step 3 is to gather the evidence that will help you make the decision. And this involves finding a test statistic and a p-value. And even though this is in chapter 11, where we're comparing differences in two population means, those means are dependent. And so we can reduce the test down to a t-test on a single measure. And so, so we're going to use the same procedures that we used back in section 10.3, and that is the t-test. So we're going to use the t-test, and the test statistic is going to be a t-test statistic. The distribution is going to be the t-distribution with degrees of freedom equal to n-1. It's the same exact thing that we did with the t-test before. And then you've got the p-value that it'll print out as well. Okay, usually in tests like this, there is a slight change to running this function, and it's going to be this. Usually you're going to be given the data values in a table like this, and then you're going to have to calculate the differences. And so the way that we're going to do this with the graphing calculator is we're going to put all of the before measures in L2 and L1, and we're going to put all the after measures in L2, and then the differences we're going to put in L3. Now you can decide whether you want to take L1 minus L2 or L2 minus L1, one or the other of those. And then depending upon the way you subtract, that will be directly related to what sign you put here in the alternative hypothesis. Now, since our numerical values are going to be sitting in L3, this is what the t-test inputs would look like. So we're going to run the t-test, and the first thing it's going to ask for is the mu0 value. I'm not sure if this comes first or the input comes first, but now in this test, our null hypothesis is always going to be the mean of the differences is equal to 0. So the mu0 value will always be 0. So when you do the t-test here, that first number that you enter in is going to be a 0. And here's the other change. Since all of our differences are going to be sitting in a list, going to be sitting in L3, and we're not going to have the sample mean and the sample standard deviation already calculated, instead of using summary statistics, we're going to use data this time. And it's going to ask you for your X list, and we're going to use L3 because L3 is where all the differences are contained. I'm not sure if they give you a frequency list here or not, but you either just leave it blank or put 1 in there. Now, this list, the calculator will then be able to, from this list, calculate X bar, SX, and N. But remember, X bar in this case is actually the D bar, the mean, the sample mean of the differences, and the SX that it gives you is the sample standard deviation of the differences. So it's going to have all that information, and the only other thing that you have to tell it is that your mean is and then you have to specify not equal to mu0, less than mu0, or greater than mu0. So there's no change here. Something about the null hypothesis at the beginning, something about the alternative at the end. And then they need the summary statistics that they can calculate themselves. The calculator can calculate if you give it all the differences in L3. Okay, so step 4 is to make the decision. There's no change there. You can use the p-value approach. You can use the classical approach. So I'm not going to specify that here. And then the step 4 or step 5 is also no change. The conclusion. Interpreting the decision. There is evidence to support the claim that. There's no evidence to support the claim that, or so on. So the big changes would be how you calculate the test statistic and the p-value. And you have to do a little bit of upfront work with the lists here. All right, so that's kind of a summary of the 5 steps of the hypothesis test from section 11.2. Let's go to an example. Maybe I'll go to the notes first. Here you can see that for a two-tailed, left-tailed, or right-tailed test, you can see that the null hypothesis is always the same. The only difference is the sign that goes in the middle of the alternative, not equal to, less than, or greater than. Here is the test statistic. Remember, it's very similar to x bar minus mu sub 0 all over Sx divided by the square root of n. This was our t-test critical value when we had a single sample. But x bar is equal to d bar. And the mu0 value is equal to 0. Sx divided by the square root of n. Same thing down here, but it's this standard deviation of the differences. And d bar minus 0 is just d bar. So it's kind of a simpler test statistic formula there. But remember also that the calculator will calculate that test statistic for us. All right, on the next page, I give you a couple of problems. And this one is called Getting Taller. And they've measured the heights of the father and the heights of the son. And you have 1, 2, 3, 7, up to 13 different pairs of father-son combinations. Now, the reason why these are dependent is because for the first family, if you have a father that's pretty tall, generally the son will inherit, it's a biological son, will inherit the genes. So tall fathers tend to have tall sons. If you have shorter fathers, like this one here, 67, this shorter father, at least compared to this taller father, also has a shorter son. So these pairs go together because of genetics. So the one set of data, that sample mean, is dependent on the other. We're taking one sample, but we're taking a before and after. Or we're randomly selecting individual families, and we're measuring the height of both the father and the son. So these pairs are linked together through genetics. And that's why making a calculating the difference and doing the t-test on the differences makes sense here. All right, so you have this somewhere, and let me get a bigger copy of it here. And we'll go through this. So here's our first example. This is from 11.2. We're going to put all the father heights in L1 and the corresponding son heights in L2. And then we're going to calculate the differences. So get your calculator out and go into Stat and then Edit and clear out list 1, 2, and 3. Right, so all cleared. You want to clear, just highlight the list and then hit clear and then enter, wipes it out. All right, in L1, we're going to put all 13, and don't let the fact that you have 2 different rows of data throw you off here. You don't want to put this in 4 different lists. You want to put all the father heights in L1 and all the son heights in L2. So it's going to look like this. It'll take me a second to put these in. You can do that as well. And 72.4. So highlighting this last one, I have 13. I'm just going to scroll through to make sure I don't have decimal, have any clearly erroneous numbers there. And then I'm going to go back to L2 and start with 74.1. So notice that 70.3 and 74.1 go together. And I'm just going to continue to enter in all the rest of these. Now, the next thing that I need to do is I've got all the numbers entered into L1 and all the father numbers and all the son numbers entered into L2, and now I have to do the difference. So you have to subtract one way or the other. I like to subtract L2 minus L1, but you can do it either way. And depending upon the way you do it, you would have to write your alternative hypothesis in a certain way accordingly. All right, so this is how you do it. This is a step that leads to a lot of errors sometimes. If your cursor is sitting right here, you can't enter a formula. And you certainly don't want to do these, one by one and, subtract them that way. So what we're going to do is highlight L3, and then we want to subtract L2 minus L1. So down in the input row, while L3 is highlighted, I want to hit second and then the number 2 to get L2, minus, and then second and the number 1 to get L1. So this first number, if everything is done correctly, if I take 74.1 and subtract 70.3, I should get 3.8 in this first number, positive 3.8. But what's nice about doing a formula is it'll calculate all of these differences at one time. And there's our 3.8. All right, so you can see some numbers are positive, which means that the son is taller than the father, and some numbers are negative, meaning that the father is taller than the son. And if you scroll down, you'll see that you have differences in, for all 13 of the father-son pairs. All right. Just for your reference later on, I'm going to enter in the differences here, just so you have it. 3.8, 2.1, -4, 2.4, -3.9, -0.2, -1.4, and so on. -0.8, 5.9, 1.5, -1, -1.8, and positive 1.5. All right, so there they are, all the differences. Now let's get down to testing to see if the claim that they've specified in here, if there's evidence to support it or not. Okay, to test the belief that sons are taller than their fathers, a student randomly selects 13 fathers who have adult male children. She records the height of both, the father and the son, in inches, and obtains the following data. Are sons taller than their fathers? So we'll turn that question around to a statement. Sons are taller than fathers. Now, all right, you have two choices here. You have the mean of the differences is negative, or the mean of the differences is positive. Now, we subtracted L2 minus L1. So we took the son's height and subtracted the father's height. The father was the first list, L1, and the son was, all right. So L2 minus L1 is what we used, or what I used. If you use L1 minus L2, then all of these numbers will be exactly the same, except they will be opposites. So 3.8 would be negative 3.8, 2.1 would be negative 2.1, and so on. Let's take a look at this says the mean of the differences is negative. Let's just take a look at an individual pair of this one here, 1, 2, 3, 4, 5, 1, 2, 3, fifth one right here. That gives us the negative 3.9. In this case, if we encounter a negative number, does that mean that the son is taller or the father is taller? Here we got a negative. Which is taller, son or father? You can see that the father is taller. So if we have the mean of the differences is negative, that would mean that the father is taller. This one here says the mean of the differences is positive. Well, let's consider an individual data pair where we have a positive number, like the first one, this one right here. This one is going to give us 3.8. We subtract 74.1 minus 70.3 to get this number. If the individual data values are positive, then you can see here that the height of the son is larger than the height of the father. So here, the son is taller. So you kind of need to go through this reasoning to decide, how you're going to write your hypotheses. All right, so we are now ready. We have alpha equal to 0.10, and we're ready to go through the steps. Are sons taller than their fathers? Well, we're going to test the claim and determine if that is the case, if there's evidence to support that or not. So mean of the differences is equal to 0. That is always the null hypothesis in these tests. And we're going to test the claim that sons are taller. And when we did this analysis here, this means the father is taller, and this one means the son is taller. We want to test this claim. So the mean of the differences greater than 0. Sons are taller. And this is the claim. Sons are taller. Mu sub d is the mean difference between the fathers and sons' heights. Step 1. Step 2 is up here. Identify the level of significance right there in the problem, as it usually is. All right, then we're going to go to step 3. And maybe I'll do that one over here. We're going to run the t-test. All right, so the first thing it asks for is the input. Many of our problems, we just circle the summary stats, but in this case, we want to select data. As soon as you select data, it's going to ask you for your list and the frequency list. But the first thing it's going to give you is the mu0. What's the number in your null hypothesis? It's the 0. Okay, so both of these are your mu0 values. Then it's going to ask you for the X list because you selected data. Now, remember the list where we put our differences? That's the one you want, and that's L3. So the X list is L3, and the frequency is is 1. And the only other thing is to specify the sign in the alternative hypothesis. And so we want to select greater than mu0. Here. Greater than mu0. And then we can just go ahead and calculate. All right, so here it is. We're going to select data. mu0 is 0. List. I want to hit L3. And I notice that L3 is right above the number 3. But it's in blue. So I have to hit the blue key, the second key, and then 3. It would look like this. Second, and then the number 3. We'll change it to L3. Frequency, that should just always be 1. And then we want to select the greater than mu0. Calculate. What is it going to calculate? Always the same thing. The test statistic is t, and then the p-value. Calculate. All right, so the t-value is 0.39. I'm just going to round it to 3 decimal places. And the p-value is 0.35, I'll call it 1. Now, I'll always insist that you write down the summary statistics. Now, notice we didn't select the stats here, so we don't know what x bar, sx, and n are. We do know that n is 13 because we have 13 pairs of son-father pairs. So they'll always give you the mean and the standard deviation and the sample size. So always write those down. The mean of the differences is 0.315. The standard deviation of the differences is 2.897. And then we have n is equal to 13. You could convince yourself by plugging into the formula this stuff in here. So if you test statistic would be d bar over SD divided by the square root of n. So d bar would be the 0.315. SD would be 2.897, and then divided by the square root of n. You can convince yourself that this number is 0.393, but that's the work that the calculator does. And this would be an approximation. Okay, so the rest of the test then is similar. Step 4 is to make the decision. And if you put p and alpha side by side, p to the left, and write 0.351 for the p-value right here. And alpha was set to be 0.10, our level of significance at the top. Clearly 0.351 is larger than 0.10, so that means p is greater than alpha, and that implies that we do not reject the null hypothesis. And then 5 is the conclusion, where we interpret the decision. So we're not going to reject. So this idea that the mean of the differences is 0, that there is no difference between the heights of sons and fathers, even though we found on average about 1/3 of an inch, that difference that we observed is not, as we call, statistically significant. And also remember, this is based on one sample. So you never want to make any broad generalizations based on one sample. Just state that there's evidence for or there's not evidence for, and then let others interpret the meaning of that. So we're going to say, since we were unable to reject the null hypothesis to show support for the claim, that's what we're going to write. There is not enough evidence to support the claim. there's not enough. Sometimes we say there's insufficient evidence to support the claim that, on average, sons are taller than fathers. So we have pre and post, before and after, matched pairs, sometimes they call it, where we're going to subtract two dependent numbers together, two dependent data values, and then do a t-test on the difference.